So here we're going to look at the geometric distribution. The geometric distribution occurs when you are carrying out successive independent trials and you want to know or you want to find out how many attempts it's going to take before you achieve your first success. If you remember, for the binomial distribution, we had a fixed amount of trials and our random variable was measuring the number of successes we might have. This time round, we have a fixed number of successes. It's one success, and our random variable is going to measure the number of trials that you might have. So the fixed and variability of the number of successes and the number of trials have been switched around. There are some conditions that we're going to need to be able to model a situation with the geometric distribution. These are going to be quite familiar to you. Firstly, we're going to expect a constant level of probability. Second, each trial, we want it to be independent. And thirdly, there should only be two outcomes, success and failure. So once again, the random variable that we're looking for, the x value that we're going to use in our probability statements, is all about the number of trials for us to achieve our first success. So you can imagine rolling a dice multiple times until we first successfully achieve a 6. Well, the number of attempts that it takes for us to get that first 6 is the random variable. Okay, let's try that example with some actual values, some probabilities involved. So here we have Johan playing a board game, but he can't actually start the board game until he rolls a 6 on his dice. What's the probability that he's able to start on his fourth roll? Alright, so let's actually get the probabilities we're working with. The probability of rolling a 6 on a fair dice is 1 over 6. And the probability of not rolling a 6, so the complement of 6, is 5 over 6. Let's just try and think this through. If he doesn't get a 6 until his fourth roll, that means the first 3 rolls he failed to get a 6. This notation is how we describe a geometric distribution, where the probability of success is the parameter. I'm just going to write these again as P and Q. So as I said, if it takes 4 rolls before he gets his first success, that means the first 3 attempts, the first 3 rolls, were all failures. So we get Q multiplied by Q multiplied by Q for the 3 failures, and then finally we had a success. Okay, we can neaten this up, tidy it up, and substitute those probabilities that we had from earlier. 5 over 6 for Q, 1 over 6 for P, and that leads us to an answer of 0.0965. So hopefully you could follow that. We were waiting for our first success, so everything before that must have been failures. With the geometric distribution, you're only ever going to have one success, since we're looking for the first success. Okay, let's see if we can generalize that. So once again, the only parameter is P, the probability of success, remembering that that stays constant throughout the whole scenario. Now, the probability that the random variable, the number of attempts needed, equals n, is going to be n minus 1 failures and 1 success. So altogether there are n attempts, 1 success, all the rest were failures. Okay, so here I actually want to show you what the whole probability distribution is going to look like. So all the possible values that x can take, which is actually going to be an infinite number. Although this is a discrete distribution, it is not finite. There isn't a fixed top number that we're working with. So don't get discrete and finite confused. You can be discrete and infinite. Okay, so here's the probabilities. There's always n minus 1 failures and one success. And this is how we would generalize. Okay, so any of these individual probabilities we should be able to pull out using that probability function. Now, something to notice is that actually the values that we have here, they form a geometric sequence where each subsequent value is multiplied by q. There's one extra q factored in for each subsequent probability statement. And this is exactly what we see in a geometric sequence. So a, or the first value in the sequence, is p, and then the ratio is going to be q. And we can do all the things you would usually do with a geometric distribution from here, such as finding the sum up to a particular value. So if you remember, for the geometric sequence, we can find the sum from the first value up to the nth value by using the form a 1 minus r to the power of n all over 1 minus r. And if we go ahead and substitute the values that I'm talking about, the values that we have here for a and for r, we end up with p 1 minus q to the n over 1 minus q. Okay, what's nice about this, and you may not see it straight away, 1 minus q is p. 1 minus p is q. So I'm going to write this all in terms, well, I'll write the denominator in terms of p. I notice that they cancel out. And I realize from here that the sum from 1 up to any specific value of n is 1 minus q to the n. And that's the definition of a cumulative probability, the probability from 1 all the way up to that value. So here's a useful statement that you're going to make use of. The probability that x is less than or equal to n equals 1 minus q to the power of n, q being the probability of failure. Okay, so from here we should be able to deduce a few more facts or statements. So let's go ahead and start with the fact that since probabilities are exhaustive, we know that the probability that x is less than or equal to n plus the probability that x is greater than n should equal 1. We'll do some rearranging from here. We're going to make greater than n the subject. Well, we've just got ourselves a function, an expression for the probability that x is less than or equal to n. So we'll substitute that in. So I get 1 minus, open brackets, 1 minus q to the n. And by expanding the brackets to simplify, we just get q to the n. So the probability that x is greater than n equals q to the n. Okay, you might want to do this a few times just to convince yourself and to make sure you're not stuck for what statement you can use when you're working with these cumulative probabilities. I can do another one. So similarly, if we start with the probability that x is less than n and we add on greater than or equal to n, we can then make this greater than or equal statement the subject, and we get a similar expression which leads to q to the n minus 1. Right, so you do really want to commit these to memory. You can always come back and deduce them from this exact starting point if necessary. But actually, it would be. But actually, I hope you would be able to see how one of them can easily be turned into the other one in the first place. Okay, so greater than or equal to n is basically the same as greater than n minus 1. So as I said, commit these two to memory or make sure you know how to deduce them from this original starting point. Okay, so here's an example that you may well get as you work through these exercises. The probability that Genevieve passes her driving test on any one attempt is 0.6, and we're going to find these probabilities. So first we're going to describe this as a geometric distribution, 0.6. The probability she passes on her fifth attempt. So that's going to be 4 failures, followed by a fifth attempt, which is a success, and we're just going to substitute those values in. Alright. Gives us an answer of 0.0154. Okay, for the second part, she needs 5 or fewer attempts to pass. So less than or equal to 5. And we can just substitute that into the function we found earlier. So that's 1 minus q to the power of 5, and substitute those in. But this makes more intuitive sense anyway. If she needed less than or equal to 5 attempts, something that definitely didn't happen was that she failed 5 times. So I started off with 1 and I subtracted what definitely didn't happen, which is the 5 failures. Okay, and that leads to 0.9898. Greater than 5, once again, we can substitute into the function that we found, or thinking intuitively, she definitely failed 5 times if she's taken more than 5 attempts. So q to the power of 5. Okay, try and make sure that these situations and scenarios that you're interpreting, you actually have a good understanding of them in your head as you're working through these probability statements. It will help to make sure that you can sense check your answers. Has the answer I've achieved, does it actually make sense in more than just one way? Okay, finally, the assumptions about the calculation. As usual, these are just statements you're going to need to memorize. Very familiar to what we see with the binomial distribution. So each attempt to pass has a constant level of probability. Each attempt to pass is independent from the other attempts to pass. Okay, so 2 of the conditions that we should be able to state. Okay, so I do want to show you what happens with a double-sided inequality probability statement. Okay, so the probability that is in between 2 specific values. Well, we should know that this is all of the individual probabilities from 20 to 21 and all the way up to 39. As we've always done, we should be able to do a subtraction of 2 cumulative probabilities. So the probability that x is less than or equal to 39, and from that we can subtract the probability that x is less than or equal to 19 to ensure that we leave 20 as part of the final statement we're working with. Because I do want 20 to be included, I subtract less than or equal to 19. Okay, so let's replace these with the statements we're starting to get familiar with. So substituting into 1 minus q to the n, and actually just processing this calculation. Being really careful with the subtraction in between the 2 brackets, we'll be left with q to the 19 minus q to the 39. So if we want, we can go ahead and generalize that as the probability that x is between a and b inclusive is q to the a subtract q to the b. Okay, even with that said, I hope you can see that actually we could have made use of a geometric sequence to try and sum the probabilities that we have here. So once again, the probability that x equals 20 plus probability x equals 21 all the way up to x equals 39. Well, since we're already happy that we have a geometric sequence, we just need to define A and R. So A would be the first probability statement within this sequence. So that's q to the 19 times p. And then R is going to be q. And we could have used that with n equals 20. It would take 20 terms to get from 20 to 39. And we can just go ahead and sum from there. So you actually have two approaches here if you have a probability statement that's a double sided inequality.